Hello, and welcome to the Chapter 16.4 lecture on triple integrals. So the double integral gives the volume underneath a surface, and it's rigorously the sum of the volumes of the rectangular solids with bases on the xy plane as the area of those bases of the rectangular solids goes to 0. And we're summing the base times height. Well, for a triple integral, then what we are doing is summing the base times height of rectangular solids that live in four-dimensional space. Now, the base of the rectangular solid is an entire cube. And then out of this cube in the W direction being the realm in which f of x, y, z lives, is the height. And think of it like a rectangular tesseract. And we're summing the quote volumes of those tesseracts as their bases go to volume 0. So that's hard to visualize. Naturally, we can't really visualize four-dimensional space, but we can think of it in analogy to double integrals. This theorem gives the rigorous bounds on a triple integral that we would employ to take the triple integral of some function f, x, y, z over a region with the given bounds. And I don't recommend trying to memorize this like a computer. Instead, draw the picture. And even if you did memorize this, you would still need to piece together which pieces go where. And geometrically, this is taking the double integral over some two-dimensional slice or region of it, parallel to, in this case, the zy plane, dz dy, and then integrating that with respect to x between the given x bounds. So the way that we'll be approaching triple integrals is to think of a nice way to slice it, and then take the double integral of that slice as the variable that we are keeping constant stays constant. And then we will be integrating that double integral as our temporarily constant variable varies. So for example, if we want to take the triple integral over this volume here, we could slice that volume parallel to the xy plane, and it would look something like this. And then take the double integral to find the double integral of f of x, y, z over this area, and then multiply each of those by little dz and sum, i.e. integrate as z varies between the lower and upper bound. So why do we care about triple integrals? These seem awfully abstract. After all, it's not even a volume. It's like a four-dimensional analog of a volume. Well, here's a nice illustration of how triple integrals would naturally arise in the physical engineering world. Suppose that we have a box of variable density, and we want to find the total mass of the box. Well, density, by definition, is the mass per volume. So that means that mass is density times volume. And if we imagine a little tiny volume cube, we can think of that as our dv. Then the dm, the little mass of that volume cube, would be the density at that point times the volume, because mass is density times volume. And then to find the total mass of the entire box, we can add together the masses at all of the little dv cubes, but adding together all of those little dm masses is the same as integrating. So we take the triple integral of both sides, and the total mass of the box is the triple integral of density dv. Okay, so let's evaluate that triple integral. The density function is this 2 minus z. And we can imagine that first we're going from z equals 0 up to z equals 1. So that's our innermost integral. And then our outer two integrals, dy and dx, correspond to the slice at each of those points, z. So that's our triple integral, and then it's just a matter of evaluating it going from the inside out. And note that for constant bounds, Fubini's theorem applies. So we could, if we wanted to, swap the order of integration, and so long as the bounds are constant, you can do that. If the bounds are not constant, Fubini's theorem does not apply. Now, at the end of 16.3, we learned this important observation that to find the area of a region R, the area is going to be the double integral of 1 dA, imagining that the height is 1, then the base times height is the base times 1 is just the base. And we typically omit that 1 and just write the double integral of R dA. Well, in the same way, the volume V of a region R will be, the volume is the triple integral of 1 dV, exactly analogous, i.e. the triple integral of dV. So we can use this and triple integrals to find the volumes of regions. So, for example, given this funny looking shape, we can find its volume. So first, we know that the volume is the triple integral of 1 over the region. So it's just a matter of finding the bounds on this triple integral. And to do that, we'll want to consider which way to slice is most convenient. So often, slicing parallel to the xy plane will not be a nice way of slicing, because then for a given z, this point here would be some kind of arc function or inverse function of whatever is going on. So this y here, in this case, would be y equals arc sine of z, and we don't want to have to deal with bounds or integrals, especially involving arc trigonometric functions. So for this reason, we do not want to slice horizontally. Instead, we want to slice vertically, either parallel to the xz plane or parallel to the yz plane. So it looks like maybe if we slice this way, that would be nice. The reason that this is a nice looking slice is that it's nice and rectangular for any constant y. So we'll be holding y constant kind of temporarily and integrating over this slice, and then taking that and integrating between y equals 0 out to y equals pi. And to help visualize this slice, let's draw the xz plane and draw this slice, and then we can find the bounds on it. So this rectangle looks like this when projected onto the xz plane. And what are the bounds? Okay, so it clearly begins at x equals 0 and is along z equals 0 as well, as we can see. And how far out does it go? Okay, well, up here in the z direction, it goes up to z equals sine of y. And how far out does x go? Well, it goes out to y equals x. So in other words, our inner integral, that would be our dz dx, or equivalently dx dz, because in this case it has constant bounds relative to x and z. So z goes from 0 up to sine y, and x goes from 0 up to y. And then lastly, dy. What are the bounds on y? Well, we can see that y goes from 0 to pi. So that is our triple integral to find the volume. And now it's a matter of evaluating that. So again, the theme and idea is to choose a convenient slice. Rectangular slices are nice if you can get them. Draw the picture relative to those axes when we hold the other variable constant, in this case y. Find the bounds given that, and you have found your inner double integral, and then integrate that relative to the variable you had been holding constant. Okay, for the sake of completeness, let's evaluate this triple integral now. Okay, so we got this triple integral. I'm not writing the 1 this time. We typically don't write the 1. I just wrote it earlier to better illustrate. But we can always imagine that there is a 1 there if there's nothing there. Okay, so that inner integral, the integral of 1 dz is z. So that inner integral is z, and we are evaluating it between z equals 0 and z equals sine of y. And we are doing that dx dy. Okay, well, at 0, it goes away, and as z equals sine y, that's what remains. So now we have this, and we continue evaluating from the inside out. The integral of sine of y dx, well, y and thus sine of y are constant relative to x, so that's integrating a constant dx, and we have x times sine of y evaluated between x equals 0 and x equals y. Okay, well, again, at 0 it goes away, so we just have y times sine of y after evaluating that difference. So this becomes the integral from 0 to pi of y sine of y dy. And that is sine y minus y cosine y, evaluated between 0 and pi. So this integration by parts we had to do for this is just Calc 2. Review your Calculus 2 integration by parts. So we wind up with that as our Calculus 2 integral of sine y times y. We evaluate between pi and 0. At pi, plugging in, we have 0 minus pi times -1. And plugging in 0, we have 0 minus 0, goes away. So we wind up with a total answer of pi. Okay, so here's a problem. The problem is to find the volume of this guy. And go ahead and try to think of how to slice it. You can slice it parallel to xy, to xz, or to yz. 2 out of the 3 of these are not too bad, and one of them will result in a mess. So pause the video, set it up. Okay, so we'll do this 2 ways. The first way will be slicing parallel to the xy. It's always helpful to draw the picture. Okay, so here's the xy axis, and at a particular z, then we'll have a parabola going up to some point. And we're looking at something like this. And how far out along the y-axis do we go? Well, we're told that z is 3 minus y. That means that at a particular z value, y is 3 minus z. And then we will go from negative root y, just because this is the parabola y equals x squared, up to positive root y. And finally, z goes up to 3 right there, because z is 3 minus y. So when y is 0, we're at 3. Okay, so anyway, our inside double integral will be the following with this way of slicing. Remember, this was the volume, so there's just a 1 there. Okay, so if we're slicing this way, that would be dx first. And we would be going from negative root y up to root y. And then dy, we're going from 0 up to 3 minus z. This guy is the double integral over this slice at a given z. And then finally, z goes from 0 to 3. So that is one way of setting it up. And this isn't too bad. Sure, it has that square root there, but integrating a single square root is not very bad. Before we solve this, let's illustrate another way of slicing. So this was slicing parallel to the xy plane. Another way of slicing might be these rectangles. Let's draw the picture. So this picture will be on the xz plane, or its projection is, rather. Okay, so here's that rectangle. And this is at a particular fixed y. Okay, so at a given fixed y, we go up to z equals 3 minus y. That's the height of the rectangle. That's 3 minus y. All right, didn't label. This is the xz plane, our projection of this rectangle. Okay, and how far out do we go? Well, we know that y is x squared, and that means that x is plus or minus the square root of y. So the amount that we go out is minus root y up to plus root y. Okay, so what does our integral here look like? Okay, we're finding the volume, so we put a 1 there. Okay, so we can say do it dx dz. Okay, so x goes from negative root y up to root y. Z goes from 0 up to 3 minus y. And y goes from 0 to, what is this point here? Well, that's where z equals 0. And that means that y is 3 at that point. So y goes from 0 to 3. Okay, so that will get us the same thing as this, just a different way of slicing. And here, for our inner double integral, we slice dx dz, but we could also slice dz dx. In this case, in fact, we can completely swap these two because y is constant relative to both. We couldn't have done that here because we had this root y on the inner one, but y was the second integral. We could not just swap these two. But here we can just swap because Rubini y is way out here. So equivalently, we can do dz dx dy, and then that would be 0 to 3 minus y, negative root y to root y, and 0 to 3. Okay, and the third possible way of slicing, which would be parallel to the yz axis. Look what would happen if we slice parallel to the yz axis. We would end up with a triangle, and that triangle would be beginning above y equals 0, and it's just kind of a headache to deal with. It would certainly work, though, if you could set it up. These are the two nice ways of slicing, though. So we have three very different looking triple integrals, just in terms of their appearance. This one is dx dy dz. This one is dx dz dy. This is dz dx dy. But all three of these yield the same result. We can compute them, but if you don't believe me, let me show you a nice resource. Wolfram Alpha, wolframalpha.com, can compute triple integrals for you. The syntax is just English. So for this triple integral, I typed in integral from 0 to 3 of integral from negative square root y to square root y of integral from 0 to 3 minus y. In this case, there is nothing there. I could have typed a 1, whatever the function is, dz dx dy. And you can see that it interpreted it correctly. And the answer is 24 root 3 over 5. So it can compute that for us. Don't become overly reliant on this, because for the second exam, and certainly final exam, which is proctored in person, you can't use Wolfram Alpha, but it's good for checking your work. Okay, and I've typed in all three different expressions that we came up with. So this was the first one. This was slicing the second way. And this one was the slight modification of that second way. And you can see that all three ways get the same final result of 24 root 3 over 5. For the sake of completeness, let's compute one of these forms by hand and see if we get that 24 root 3 over 5 that the Wolfram Alpha evaluated it as. Let's do this one. Okay, so that slicing was this. Let's evaluate that. So remember, if there's nothing in here, we can imagine that there's a 1 there. Integral of 1 dx is x, and x evaluated between root y and negative root y is 2 root y. Because we plug in a root y into the x and subtract a negative root y, that's adding a root y, we have 2 root y. Okay, now we integrate that dy. So remember that the way to think about root y, think about it as y to the power of 1/2. If we integrate y to the 1/2, then that means that we increase the power by 1, that's 3/2, and then divide by that. So the integral is that. Okay, so that inner integral there is this. 4/3 y to the 3/2 evaluated between those 2 points. So plug in 0 goes away, plug in 3 minus z. We have 4/3 times the 3 minus z to the power of 3/2 dz. And fortunately, this isn't bad to integrate either. It's just a chain rule. Integrate the power of 3/2, it becomes a 5/2. We divide by 5/2. So 4/3 divided by 5/2 is 8/15. And by the chain rule, the negative z makes us stick a negative sign there. So the integral of this is negative 8/15 times 3 minus z to the 5/2, and we're evaluating that between 0 and 3. Plug in 3, it's 3 minus 3 becomes 0, and then we're subtracting negative 8/15 3 to the 5/2. So we have 8/15 times 3 to the 5/2. 3 to the 5/2 is the same as 3 to the 2 plus a half. That is the same as 3 squared times 3 to the 1/2, i.e. 9√3. So this is the same as 8 times 9√3 over 15. And that simplifies to 24√3 over 5. Okay, hopefully that was instructive for thinking about triple integrals, how to set them up, and the various ways that you can solve the same problem through different slicing methods and choosing a nice slicing. Have a great one.